Professor Ravi Prakash Rao. Just a quick introduction. I mean, it's a little, this time it's really a formality because Ravi has been visiting RRI for the last 51 years. And so I think, but then the problem with that is that some of the people at the back may not still know you, given that you have not visited us for 5 years. So I'll do this one paragraph introduction anyway. So Ravi is a professor of physics and astronomy at the Louisiana State University, Baton Rouge, USA. So he did his BSc Physics Honors and MSc degrees in the 1960s from Delhi University, and he got his PhD in 1970 from the University of Chicago. He was at New York University and TIFR Mumbai before joining LSU in 1974. He has been at various universities in Australia, Germany, and India during sabbatical visits and has been a frequent visitor at RRI since, as I mentioned, 1973. He's a theoretical physicist, primarily in optics, physics, atomic physics, and quantum information. Over the last few years, of course, my group has, and my group members, and earlier group members who he knows very well, we've all had this privilege of collaborating with him on problems of mutual interest in quantum information. And of course, it is with great pleasure that we are hosting him again after 5 years of, as he calls, COVID break. So I think we have seen him 5 years ago at RRI, but it seems like only yesterday. One thing that is remarkable about the two people in the front, Professor Krishna Kumar and Professor Ravi Rao, is that every time you see them, they seem to be aging backwards. And so we are working on manipulating sudden death of entanglement, which is a time dynamics problem. And so he knows dynamics very well because he goes backward in time in terms of how he looks. So we welcome you back, Ravi. You don't smile. And of course, look forward to your colloquium. But before I end, I would like to say that, as you very well know, I have to leave. I'm a Cinderella today. I have to leave at 4:30 p.m. So Sadiq will take over and do the Q&A part and also present him with the book, right? So,
thank you very much. Thank you. Well, it's a great pleasure for me always to be back at the Raman Research Institute. I think of this as my scientific home in India. I actually gave a colloquium talk here in April 1973. And it was almost the time when it was just reopened after the institute had been closed for some years. I've been coming very regularly, as was mentioned, but now after a 5-year lapse, I'm here again. And of course, it's a great pleasure now that we are also working together on a physics problem with this beautiful experiment that Urvashi Sinha and her group have been doing for some years now on entanglement, quantum entanglement. So it's a pleasure again to be here, and actually, among things that were mentioned, I was here during a sabbatical as well, and that was when the training program of the various institutes, RRI, IISc, and the Indian Institute of Astrophysics began. And so I was one of the first lecturers in that program that RRI started at that time, so for PhD students. So it's, please come in. It's always nice to see students, and I'm here this whole week. So besides, of course, this afternoon, later on as well, please feel free if you have any questions, you want to discuss anything. I'm sitting in Professor Sinha's block there next to the library building on the 3rd floor, and please come with any questions. Okay, for today's talk, I'm going to talk about something that, as you have seen already from the title, is going to be in 2 parts. There are also lots of puns one can make about this. I think Bohn allows himself to be punned on. And so there are 2 parts to this. The first one is, of course, the question of the second Bohn approximation, which I'm going to talk about, of course, and introduce. And in electron atom scattering and many, many scatterings, this Bohn approximation is one of the common methods for calculations that we have. So I'm going to talk about that. And actually, I'll talk about it even more broadly in general in terms of electron-atom interactions, both in its fundamental aspect and in many, many applications that electron-atom interactions, of course, play. So that's going to be the major part of the talk. And in particular, one theme in it is going to be, as you can see from the title, the second Bohn, because the Bohn approximation, you will see, is a perturbation series. And The first one, of course, is what we first think of, but the second one is actually the one that is more important. And it's a very peculiar situation already. So I'll talk about that as well. So this is an example in which the second term actually dominates over the first in a perturbation expansion. And in particular, the process I'm going to talk about, there are many in the audience here who themselves do experiments in charge transfer and so on. But the one that I'm going to talk about is what is called charge transfer between an atomic or molecular ion and a neutral atom. So a positive ion comes and hits the neutral atom, and it grabs one of the electrons of the A onto itself. So it goes on as a neutral B, and then, of course, leaves behind a positively charged ion. So this is charge transfer or electron transfer. And I'm going to talk about how at high velocity, if you look at this charge transfer into the forward direction, it's actually the second-born term which is going to prevail, and not the first-born. Now, the second half of that title is something that I'll start with one slide, and that is a completely different story, it seems to be. And it's something which has to do with what happens if you want to turn a big ship around efficiently when it is going in the sea. And there is a maneuver, I'll talk about this in the next slide, which goes by the names of the two people who came up with it. And it turns out that, for instance, this maneuver, which is taught to people when somebody falls overboard, and you want to sort of course, pick him up, pick him or her up, rescue, and how do you do this most efficiently? And the interesting thing is that there is an intimate connection between these two problems. The second problem, which one doesn't even think of as a physics problem, and the second one, which is certainly a quantum physics problem and somewhat sophisticated in that it's the second term that actually dominates. But as you will see, the two things are connected, and that is why this talk. Okay? All right, so if I can get this to work. I'm always suspicious of these things. Okay, but anyway, so here it is. So let me start with that maneuver. What is this maneuver? And it turns out that this is a maneuver that actually I came across when I was reading an essay in The Atlantic, which is just a magazine. And there is a writer called John McPhee that some of you may know. He's a very good writer. He writes on a variety of themes, particularly in geology. He's himself not a geologist, but he's really very, very good at it. And there are a number of books of his on geology, geophysics. And this is John McPhee. He's in his 90s, but he's still writing. And he had this article on, which was called The Ships of Port Revel. Port Revel is a place in France where they train captains and other officers of ships in various things about maneuvering at sea. And one of the points in that article was that in the 1903 Russia-Japan war, a Russian officer called Butakov apparently came up with this idea of how to turn a battleship around to use the guns on the other side. So you have guns on both sides. Think of them as old-fashioned cannons or these modern guns, and you're firing at the shore, and then, of course, you've exhausted, and then you want to turn around, and then in the meantime, of course, the other side will be loaded. So they wanted to do this as efficiently as possible. And that's when he came up with this maneuver. I'll get to the maneuver in a minute. And now, quite independently, in the Second War in the Pacific, an American officer, Williamson, came up with independently the same maneuver to rescue somebody who falls overboard. Okay, so that is the Williamson-Butakov turn. And the point is the following, that if you think about it, say, for instance, somebody falls overboard at this point, and the ship is moving along, and it wants to, of course, pick him up. So the natural thing you would think of is come to a break your thing, come to a stop, turn around, and come back. Now, it'll be interesting, particularly for the students, that if you put in little numbers, as I had to do for this talk, it's really quite dramatic. In fact, many of you will probably appreciate this, that the time that it takes to come to a stop, given an acceleration a, is, of course, something that we all know. The time would be the velocity divided by a, and the distance traveled would go like v squared over a. Now, both these numbers, of course, depend on the speed with which you're traveling and on the acceleration. Now, a good term in terms of which, as physicists, we can talk about acceleration is, of course, little g, the acceleration due to gravity, and this is a number we're all very familiar with. And it's helpful to think of it as, say, 36 kilometers per hour per second. Now, most of our accelerations and decelerations are actually of the order of this little g. So if you think about it, if your car is going about 30, 40 kilometers per hour and you slam the brakes, in 1 or 2 seconds you will come to a stop. Okay. So it's not quite g, but the accelerations are maybe 1/2 or 1/5 of g, but it's of that order of magnitude. The same thing when you think about a plane. In taking off, it has to reach a couple of 100 kilometers per hour in about 2 kilometers, let's say. And again, you put in the numbers, you'll see that the accelerations are of the order of little g, a little less, always, 1/2, 1/5, that kind of number. But if you take a big ship, whether a battleship or whether one of these big container ships of today that you're all familiar with, then it's really remarkable that the best accelerations or decelerations they have are 2 or 3 orders of magnitude smaller. So a big ship, in fact, I think you've all heard the term, the way it comes to a stop, if it wanted to, is to reverse the engines. So you have the engines and you just sort of turn them around, reverse the engines, but it still takes a very, very long time. Typically, these are huge ships already. They'll take about 12 or 15 times their length before they come to a stop. So it's not really a very efficient thing to jam the brakes at this point where the guy fell overboard and then come back from a certain distance. So the Williamson-Butakoff solution for this is a very interesting one. And that was that you don't change your speed at all. Keep going full steam ahead. But at this point, you rapidly start turning your ship. So you turn your wheels as far as you can, and of course the ship is going to start swinging, and it's going to swing. And when it has reached 60 degrees to the original direction, then you make a rapid swing in the other direction of your rudder, and of course of your wheel, and then it'll execute a loop like this. I'll come back to some details later on, but the net effect is going to be that it's going to come to a point at this place. Remember, it's keeping the same speed, magnitude v, all through, but it'll be pointing in the opposite direction. Okay. So the velocity is reversed in a very efficient way by doing these turns. At 60 degrees, there is a turn, and then you make another turn so that you complete that loop, and that is the Williamson-Butakoff turn. As I said, I'll come back to this at the end, but keep just in mind now that there are these 60-degree turns that are apparently the most efficient way to rescue somebody at sea. Okay, now let's leave this for a minute and go back to the physics problem, the physics part of the talk, and that is about perturbation theories. Now, perturbation theories, even beyond the Bohm approximation or in scattering problems, are of course all over physics. And it's clear because exactly solvable problems, there are only a few. For Newton, for instance, he knew that the sun planet he could solve, but any other planets, any other disturbance, these are immediately make the problem not exactly solvable. So there are, of course, methods that are developed. In particular, you think maybe the other planets make only small disturbances, so they're weak effects, and this is the idea of what is called perturbation methods. So perturbation methods go back to the beginnings of physics. And of course, in quantum physics, the same story. You have the two-body hydrogen atom problem, which we all know how to solve exactly. But you add even one more electron, or you add an electric or a magnetic field or something, it's no longer exactly solvable. But again, the idea would be that if in some way these things are only small changes that they're going to make, then I can use perturbation theory, and of course you develop perturbation methods. Now, Newton already has perturbation methods in the context of quantum physics. Schrödinger is the one who first developed some of these perturbation series, and in fact, it was for the problem of an external electric field on the hydrogen atom. Okay. Now, so the idea is that you have a part of the problem which you identify as dominant, and you know how to solve it, this H naught. And then the other part is some kind of weaker thing, and let's call that an H prime. And whether you are interested in energies or some transition from some quantum state n to another state m and so on, doesn't matter. There'll be some leading term which you can get from the H naught, but then you take into account in some ways the perturbation. I've just put sort of schematic brackets, but many of you will recognize the connection to our quantum terminology. And so this is one order of perturbation, H prime. And of course, if you want to go further, you would do the same thing by taking the perturbation acting, so to say, twice. But now, as you can see immediately, this is going to be much more complicated, because in between now, there can sit all the states in the system. And typically, in our electron atom or any of these contexts that we look at, there's an infinite number of things that can go and sit in the middle. And so this is why second-order terms are very difficult to calculate, often are not done. And if you can stop at the first order, then, of course, you stop at that. Okay? And, of course, you hope that if the whole thing is going to be meaningful, so your initial assumption that this is only a small change that is going to be made, you want, of course, successive terms to get smaller and smaller. So as you go up in a perturbation series, you would, of course, want the later terms to get smaller and smaller. Now, this is not very important for the talk, but let me just mention, since I have it here, that, for instance, the hydrogen atom in an electric field is a very good example, where at first, actually, and this is what we all do in our classes, you can solve the first order, the second order correction, this is your polarizability, and so on. And people actually already in the 70s, with the computers of that time, were carrying it out to 25th order and so on. And what they found was that even for very weak electric fields, that series does not even converge. So initially, it looks like it's getting smaller, but then it starts growing, and it's really a divergent series. And so it, in some ways, doesn't even work, but on other ways it works, but I'm not going to get into that unless somebody wants to discuss it later. Now, the same thing is true throughout perturbation methods, including, for instance, in field theories. There is the famous QED, for instance, where the perturbation parameter is a natural parameter formed out of these fundamental constants, the fine structure constant. And since it's of the order of 1%, you can hope that indeed if you make a perturbation series now, so this is 1% compared to that, then the next one will be 10 to the minus 4, and so on. And so that is your QED series. Now again, the question is quite open whether the QED series is convergent or not. In fact, the best we do today when we do these calculations out to 8, 9 decimal places is to go up to something like the 6th or 7th order in the fine structure constant, and that seems to work very well. We compare with experiment, but actually, technically, that series is also probably not really convergent. It's really a divergent series. So there are all these mathematical questions, physical questions, which I don't want to get into. But let me just give you a very simple other one that I think is a little point that students should also sort of almost remember, is that the lowest order, which is non-trivial, is of course what is important, because sometimes the first order may actually vanish. And in fact, we know many examples where this happens. In fact, the ground state of the hydrogen atom, if you think of the electric field, because of what we call parity conservation, of course the first order term is going to vanish. So then, of course, you do the second order, and this is exactly what we do in our courses. We show how to do that second order. This is why it will be proportional to the electric field squared, and the proportionality constant is your polarizability. So Rydberg atoms have this huge polarizability, and so on, is of course part of that. Okay? Now, so there are these selection rules, and in transitions as well. So in atoms, for instance, the dominant transition is what we call an electric dipole. And so, for instance, if you take the hydrogen atom, instead of being in the ground state, suppose it's in the excited state, n equal to 2, and if it's in the 2p, now all the rules allow it to decay by electric dipole, and this is your famous Lyman alpha transition. I'm speaking in an institute which has a big component of astronomy. Of course, the Lyman alpha, the 1216 ultraviolet line, is the basis of a lot of astrophysics, because hydrogen is, of course, the dominant species. And this is the main transition from the 2p to the 1s. And that actually has a decay in 10 to the minus 9 seconds. That's typical of atomic lifetimes when there is nothing to forbid it, no selection rules. And that's the kind of number that you get in nanosecond or even smaller. Whereas, as all of you know, there is a companion to this 2p, which is actually exactly at the same energy, that's the 2s state. But that 2s state now cannot decay because it violates this parity change. There has to be a parity change if you have an electric dipole, and here there is no parity change. So in fact, this actually decays only by a second order term, which involves the emission of 2 photons. And this 2-photon transition, actually notice the difference, 1/7 of a second, instead of 10 to the minus 9 seconds. So that just shows you how much smaller the second term is relative to the first in things like this. Okay. Now, incidentally, this is again something I could almost give a whole lecture on. This is a very interesting transition, this so-called two-photon transition. It has played a role very recently in actually even the identification of anti-hydrogen. That is, you take an antiproton and you trap a positron. And so you have an antihydrogen, which of course should behave exactly like hydrogen. And in fact, the way they confirmed it was to do a two-photon absorption from the ground state to the 2s state. And it's of course the same 1/7 of a second. But anyway, that goes far from my topic for today. Now let's return to scattering, which is going to be what I'm going to talk about the next. So these are bound state transitions I'm talking about. Now let's look at scattering. Now in scattering, the dominant perturbation technique is called the Born approximation. And it was, of course, given by Max Born. I'll get to him in a minute. And it's also the first term in a series. So you really should think of a first Born approximation, a second Born, a third Born, and so on. Now, in scattering, this business of taking all the states in between is even more complicated. So there's hardly anybody who will do a third Born calculation. I've never seen one, actually. Second Born even is very difficult. And people do that, of course. We have now numerical techniques and so on. You can do some second Born calculations. But really, almost all the time, you do the first Born. And in scattering, there's no particular reason why it would be 0. So there's no such thing as that selection rule counterpart. So this is where we usually stop. So the first Born approximation is what is used. And I'll go to that in the next slide. But the Born approximation was invented by Max Born in 1926. Incidentally, many of you, of course, are also familiar with the term the Born-Oppenheimer approximation, which was done roughly the same time when the American physicist Oppenheimer visited Max Born in Germany for a few months. And that's an approximation which is used routinely throughout molecular physics and in other contexts as well. Okay. So let me now go to the Born approximation. So here's a picture of Max Born and roughly the time of the work that he did in 1930. And I put this for this particular audience because this is a picture that was taken when Max Born spent 6 months in India in 1937 in Bangalore as a guest of C.V. Raman. Raman, of course, at that time was at the Indian Institute of Science down the road. And this is a picture of Max Born and his wife wearing a sari and a turban. Okay. Now, actually, it's an interesting story because there was even some talk, note the date, it's around 1937. So many German physicists, Max Born himself was not Jewish, but his wife was, were considering leaving Germany. And Max Born had some ideas of coming and settling down, for instance, in India, which, of course, at that time was British India. Now, it didn't work out. I think it's unfortunate for us, because you can imagine the change it could have been if Bangalore had become a center of quantum theory as well in those days. But anyway, he went back and he settled down in England. And then after the war, of course, at some point, he went back to Germany. So this is Max Born. And the part of the actual story is that I think many of you know this part of the story. You've heard about this, that Heisenberg invented quantum mechanics in 1925. Notice I said 1926 a minute ago, and I'll come to that. And Heisenberg was actually concerned with what is the absorption or emission coupling between an n state and an m state. Remember, Bohr had explained the hydrogen atom and other atomic structure in terms of the various bound states. So the next natural thing was to think about the coupling to the electromagnetic radiation and these transition probabilities, or equivalently, some of you will see the term oscillator strength. And he was manipulating these things. He wrote up his notes. And like many of you students here, he wrote up his notes and he left them on this Professor Bohn's desk and went off on a 5-day hike. Now, Max Born, in looking at this, he was on the previous slide, along with his postdoc at that time, a man called Pascual Jordan, these two people, of course, figured out exactly what, in a way, Heisenberg was groping towards. Heisenberg had not even known about matrices. So he did not recognize that what he was doing was really matrix manipulations. And of course, Born knew, and Born and Jordan worked this out. And there's a famous paper of theirs in 1926. And it's often referred to, and particularly historically, I've met physicists who say it made a huge impact, and they always refer to this in German as the three-person, drei Männer Arbeit, three-persons work. Now, in that time, it's again interesting sociologically and historically that theory papers written by more than one or maybe two people were extremely rare. So to have three people write a paper was actually already something to think about, and everybody labeled it as the three-person or the three-man paper. And it's in that paper that for the first time, it is Max Born, of course, who recognized what is going on, the commutator appears, which is, of course, central to our whole field. It is not in Heisenberg's paper, but that is the origin of the H-bar in quantum mechanics. And it's also interesting, as you will see in the next slide, incidentally, here again are the pictures of these two men around that time of their work. This is Pascual Jordan, this one is Pascual Jordan, and this is Werner Heisenberg in roughly the same time. Now, the other person whose name I have to mention here, as I talk about electron atom scattering, is another German physicist who also went to the States at that time, and this is Hans Bethe. Now, Hans Bethe actually had submitted for his what is called the Habilitation, which is like a PhD, a little advanced degree, and he had submitted in his Habilitation many of the things that today we attribute to various people. And I won't go into all this, but some of you will recognize we talk about the sum rules and we associate the name. I'll only highlight for a minute this name Thomas, because it's going to occur in another context in a minute. But the idea that the total number of electrons that are there to couple to the electromagnetic field, that you know from the start. So if you have the iron atom, I know it's 26 electrons. Now, maybe there's a new mechanics now where it distributes for each electron, depending on the transition it's making, how much of the oscillator strength goes into it. But that distribution notwithstanding, if you were to sum over all of them, it must give me 26 electrons. Now, this is an extremely important guiding principle to people who were formulating the new mechanics. And all this was actually already in Bethe's papers. And Bethe also had what is now called the Born approximation. It's actually very interesting to listen to some of these historical archive records of Bethe's. The American Institute of Physics has them on record. And there's a place where he speaks about it, and he says, people said, oh, that's the Born approximation. And he had never heard about it. This is something he was using. And as he says there, he compares it to a fairly famous French play about a Jean Talhomme, who suddenly discovers when he's grown up that all along in his life he's been speaking prose, and nobody had told him. So it's a bit like that. So Bethe reacts by saying that he was using this Born approximation without having known what it is. But I think it merits that we think of it as the Bethe-Born approximation. And now let me turn to the part about the electron atom scattering, where we use this Bethe-Born approximation, and there are various further advances which have been made in recent times. And again, I won't go into any details, but there are these various names, and with today's computers, you can do more and more sophisticated calculations. But the first Born approximation, or the Bethe-Born approximation, is still very, very important, as you will see in the next slides as well. In a number of course, fundamental understanding of electron atom scattering, but also in many, many applications. There are many, many natural and lab phenomena, planetary atmospheres, plasmas, low temperature plasmas you use for microelectronic etching and so on, and certainly in all radiation effects, whether it's in dosimetry or in treatment and in biomedical applications. These cross sections for electron atom are extremely important. And the point is the following, that even if you're starting with some other initial thing like X-rays or gamma rays, we all know that you have radiation treatment with photons, X-rays and gamma rays, but the first interaction of these X-rays or gamma rays leads to an ionization, and then there's an energetic electron. And this electron then can cause other ionizations. And so these so-called secondaries go on to further excite and ionize, with the result that really you can't separate the importance of the electron-caused interactions. And as a simple, again, rule of thumb, if you have a 5 capital MeV alpha particle, which say goes into water vapor, by the time it comes to an end, it comes to a stop, there'll have been about 100,000 ionizations it has created. of electron with the ion companion. And if you count, you'll see that about 50% come from the initial alpha, and the other 50% from the electrons which are born in the cascading secondaries. Okay. And incidentally, it's also a good rule of thumb that a 5 or 2 MeV, a 5 or 8 MeV alpha particle is essentially the same as the same considerations for a 2 capital MeV proton or a 1 kilovolt electron. So a 1 kilovolt electron going in, again, the point is that there'll be a large role of not only that initial electron ionization, but all the secondaries as well. And now what is interesting is that the first Born approximation actually, again, is fairly reliable if you're at energies larger than these. So that's why I picked these numbers. So if you have more than a kilovolt electron or more than these for a proton or alpha, the first Born is actually pretty accurate. But a large number of these applications actually require somewhat smaller energies, 100 electron volts, 200 electron volts, and so on, leave alone even lower. And for that, the first Born approximation is not adequate. And this is where various advances, which we consider as Bethe-Born, have been used. But let me just say first that the first Born approximation has an alternative name that you will sometimes see. It's called the plane wave approximation, because the idea is very simple. The initial free particle of a certain momentum, h bar k, and an energy is considered as a plane wave. So the surfaces of constant phase are planes perpendicular to the propagation. And what Born was looking for in 1926 was to get an idea of what the wave function would mean in the scattering context, not just what Bohr and Heisenberg were concentrating on the bound state sector of the problem. And so he said that there is this plane wave, and in some way the scattering, of course, adds to it some additional outgoing waves, as we say. These are outgoing spherical waves, and then all the rest is some kind of scattering amplitude. And indeed, to get an interpretation of what this wave function represents, this is also in the 1926 paper. So simultaneous with the first appearance of the commutator is the probability interpretation of modulus psi squared, which we're so familiar with. Again, some of you may know in the history of the subject that there are some peculiarities even associated with that, but again, let me not get into it because it'll take me a little further astray. But here is the way it works. So you have an incident wave of a certain momentum, k, and then finally, of course, it's going out, and in a first order perturbation, so the entire interaction here is only perturbing weakly, so this is also a plane wave, and then you take a first perturbation term, which is the diagonal matrix element of this, and as you can see immediately, that is essentially the Fourier transform of the potential. So in a sense, the first Born approximation applied to this elastic scattering is a direct readout of the potential, its Fourier transform. So it gives you what this V is, and it's also very simple with a 1 over r potential, as in Coulomb problems or in gravitation, 1 over r Kepler-Newton problems. This is easily done, and it has this famous 1 over k squared, which, of course, on squaring is the famous Rutherford scattering, which drops off like v to the minus fourth, and because of that angle, it is very sharply peaked at small k. Now, if on the other hand, you have not a point charge, as in Rutherford scattering, but you have an atom, then of course you also have, in addition to this 1 over k squared, you have the matrix element of that e to the I k dot r between the initial state, let's consider that the ground state, and whatever state you end up in. And so that would be your first Born approximation for the scattering amplitude, and it'll depend, of course, on the angles and so on. Another word that you'll encounter often in physics is these things we call form factors, and that is where we get all the information about the actual collision or what is going on. So these are things that we measure, and then we try to infer what this potential is, which is responsible for it. So that is the game we are always playing. Now, again, there are various curlicues on that I won't go into, but the second Born would be something to do very similar, but now you would have to do the potential twice with all the intermediate states in between. And this is what I said is extremely difficult, and so often people don't do that. And as I said, the first Born is fine for greater than 1 keV. The second Born and so on are very large and expensive. And since we need a huge number of applications in the roughly 100 eV range, it has turned out, and this is a game that many of us have played, using the Bethe-Bone and other sort of variants and scaling methods, as we call them. And just to give you a flavor of this, I've just included here, recently with experimental colleagues in Japan and in Australia, we wrote a review article on the status of all these electron atom and electron molecule collision cross-sections as done in the Bethe-Bone theory. And as I said, these are very important because for small molecules like CO2, which is of course a greenhouse gas, it's the dominant component in some planetary atmospheres. Then you think about things like the nitrous oxides, again, for greenhouse gases. CF4, carbon tetrafluoride, is a gas which is used for low temperature plasma etching. It's also important as a greenhouse gas along with its companion, the carbon tetrachloride. Water, of course, which is for radiation dose, for biological cells and so on, and to simulate any living tissue, benzene, and a whole variety of these of interest. And again, details are not what I'm interested in. In fact, I skipped something. Here is what I wanted to just point out, that this is electron helium in this range of a few 10 to, let's say, a kilovolt. Above a kilovolt, the first bone is quite good. But in this range, actually, it does, in fact, overestimate. And so this tells you what these current Bethe-Bone and so on that we talked about and the experimental situation. This is an electron helium, and this gives you a more complicated molecule like CF4. And so this is the state of the art that we have now for electron atom collisions. Now, I'll skip over this. This is, of course, CO2, but we have a variety of these that have been gathered in that review article to show you what is achievable today experimentally and theoretically for this range of great interest. But now let me get to the second bone story as it applies to a particular part of this electron-atom interactions, which is this charge transfer I said in the first slide. So we are considering an ion coming on an atom, picking up an electron, and at high speeds, at high V. Now, the electron capture, of course, can take place in a variety of ways. Now, I know that there are many in the audience who actually do some of these experiments, but I'm not going to talk about most of these, like radiative capture, capture into Rydberg states, and so on. But I'm going to talk just about the direct capture. And I'm also not going to treat identical particles of B and A when, again, some other considerations come in. But if you consider a general situation of this kind, where a light particle has to be captured from the A by that B, and if you look at it, it turns out that if you apply the first bone approximation to it, it gives you a result that at high speeds, it actually drops off as V to the minus 12th. Rather small cross sections, and they drop off very fast. Now, you can sort of understand it, because if you thought of this classically, if a big cannonball comes and hits a very light ping pong ball, you all know what will happen. The ping pong ball will just simply shoot off in the forward direction with very high speed. There's no chance of this cannonball capturing that. So in fact, in classical scattering, it wouldn't even happen. Quantum mechanics is different, because this cannonball, this electron now, is not in a specific radius or orbit or anything. It has all kinds of momentum in it, including some very, very high momentum components. And that's a way of saying when the electron is very, very close to its parent atom A. And it is those which can still contribute. So the first bone is not 0, but it's still very small, and it drops off like V to the minus 12. However, in 1927, again, follow these dates. So this is immediately after the Heisenberg-Bohm papers. This man, Thomas, here's a picture of him around that time. He was an English physicist, very, very versatile. I think some of you will know the name, and I mentioned already the Thomas Fermi model, or the Thomas Reike-Kuhn sum rule, and here is L.H. Thomas. He is also the one of the Thomas precession, and computer scientists know him very well because he invented some techniques for efficient diagonalization of tridiagonal matrices. But for our story, what Thomas thought of was that in this collision for charge transfer of an electron to a mass m1, it isn't going to happen if m1 simply hits that electron. What it must do is it hits the electron into various directions, of course, but in particular, if it hits it in such a way that then it collides with its parent ion of A, and then that one turns it around, then you have a chance of matching both the speed and the direction of travel. And he figured out that if you do two 60-degree collisions of this kind, then in fact there can be an efficient match between the electron and the ion which is still flying off in that direction with almost no change, and that is why the capture is going to take place. And he worked out just on classical terms, I'm sorry, I'm going way ahead. He worked out in classical terms that this will give you a cross-section which will drop like v to the minus 11. Now, notice the power. It's also small, but 11, of course, is a smaller number than 12, with the result that at high v, it is this one which will always dominate over v to the minus 12. So this calculation of Thomas, which is a classical calculation, let me go back to this for a minute. So the Thomas cross-section in the first bone, in fact, it was calculated in great detail. There are actually some angular momentum dependencies as well. But when quantum mechanics came along and people like these calculated it, they were all getting that minus 12. And it is said that even people like Bohr were quite astonished about the Thomas result, and they thought it can't be right. It must be because he's using classical mechanics. Quantum mechanics, this must be the correct answer. And even up to 1950, remember this was from 27, even for 25 years or so, people did not quite believe it. They thought there was some subtle interference effects and so on. And again, part of the story is that a PhD student at Carnegie Institute called Driscoll in 1955 decided to take Thomas seriously. And he said if Thomas said that there is a double scattering, the counterpart in quantum mechanics should be a second bone approximation. So he worked out the second bone approximation, and indeed, later on, and found the v to the minus 11 already. And then, of course, other people did much more of these, very elaborate with other particles, various potentials, and so on. And today we know for sure, with a lot of other work done by this group that I was a postdoc in the 70s, in the early 70s, that the second bone is actually what dominates over the first bone with this v to the minus 11. Of course, the natural question is, what about the third bone or the fourth bone and so on? Now, that convergence is still open. Most likely the bone series also doesn't converge. But these people were very good at putting what we call bounds, and they actually established that the dominant for this particular process is indeed the second bone's v to the minus 11. And that has now been amply verified. I'll get to some of that in the next. And here is the Thomas mechanism done as a freshman physics illustration. And so I'm going to consider B plus on A going to B plus A plus. And so here is my big mass, comes and hits that little electron, shoots it at some velocity, and then that scatters again and comes out. And I want to have these velocities match. But this is, of course, going to get deflected very, very slightly. And I want to have these two match. And all I did in this little exercise was to do this like a freshman physics problem of two collisions. And I just applied momentum and energy conservation at these 2 points. And if you do that, as you can see, there are 3 vector unknown quantities, 2-dimensional vectors, 6 unknown quantities. You apply 2 momentum and energy, 2 momentum energy. You have 6 equations. You can solve it. And when you solve it, emerges that this angle psi is actually that 60 degrees that Thomas had intuitively thought of. Okay? And it comes about in a very interesting way. It's just the inverse cosine of 1/2. There are 2 momentum conservations, 1 energy conservation. It's amazing. Out of that comes this 60 degrees. And with that, then, you can work out the cross sections. And again, I won't go into the details, but there is a v to the minus 11, which is the Thomas scattering cross section. Now, of course, all these things inside what is going on and these trajectories I've drawn, I'll come back to that at the end, are really not there in quantum physics, or for that matter, in classical physics. But the point is, for instance, this is certainly an observable. That is the small deflection that the ion suffers, and then it has captured the electron. So the way the neutral B is coming out, and that angle is extremely small. Because of the ratio of the masses being very small, it involves a sine of 60 degrees, and it turns out to be about 1.6 arc. This is now called the Thomas angle, and in fact, it has been measured experimentally. along with other details. There is a cusp in the cross-section and so on. So those are all sort of measurable quantities which are pointing to the correctness of this picture, including the 60 degrees, which really is not accessible at all experimentally. Now, before I conclude the actual story, let me just give you, for again, this is an audience where there are people from astronomy, and so there are gravitational analogs of this that you can work out too. So for instance, a capture of a planet by an intruding star or a neutron star becoming a binary component, and in fact, it's almost trivial. You just do a dictionary translation from the charge to the mass part, and then you can work out these various what are called capture cross-sections and direct capture and so on. Okay. And in a heavy context, so for instance, instead of electrons, suppose I have a proton hitting methane or CH3, the one just before, then H2 plus, so now it's capturing a whole hydrogen atom, ending up as H2 plus, and this remains as TH2. Now, of course, the kinematics is slightly different because the mass ratio is roughly 1, and the angle turns out to be 45 degrees at which H2 plus emerges. And this, again, was first sort of calculated by these people in England, and then it was verified already long ago by beams of H plus on CH3. So the Thomas mechanism certainly works, and it works in very, very widely different contexts. And so now with that, let me make the connection to the first slide of the Williamson-Butakoff. And the Williamson-Butakoff turn, now you should really think of it in the following terms. So I had got this loop that I said is part of what they devised. But if you really think about it, what it is that there are two circles of a certain radius r, which are tangential to that line of travel, and they're also tangential, they're oscillating here. And then you can see that what goes on is the following, that you start traversing this first circle, and when you have reached the 60 degrees, this tangent, of course, is at 60 degrees, then you start making the other turn. So there is this tangent, which would also be at 60 degrees, and it is this combination which ends up at that point. Now, of course, if I were to repeat the turn at this point, you would do exactly the same. You would go like this, and you would come back to the initial position. But then you would have the same velocity direction. You wouldn't have the opposite. And remember, I said that Butakoff initially had in mind he wanted to be opposite so he could fire from the guns on the other side. But basically, you see this connection of 260 degrees playing a role in both this simple sort of mechanics, if you wish, there is mechanics, there is physics here, problem, and the second born, which is a fairly sophisticated quantum mechanical. And now you can ask, why is there such a connection? Certainly for the students at the back row, the point is that there are no trajectories in quantum mechanics. Certainly in quantum mechanics, there are no trajectories. So as I said, all the things that I showed before in this analysis, this is simply not there as real trajectories. But even classical physics, if I was thinking of these as billiard ball collisions, which is what I did for the algebra, I never really used those trajectories. So none of this really matters, because what is going on is simply that you're applying the laws of conservation of momentum and energy. And those, of course, are valid. They're valid in quantum physics. They're valid in quantum physics down to the individual quantum event. They are never violated. And that is the reason why these things work. Trajectories themselves are sort of aids to our imagination. They're part of our classical intuition. It's important. We, in fact, are classical creatures. We're going to use our classical intuition. And Thomas's classical intuition clearly paid off. Even for 25 years there, the quantum mechanics was saying something different. And so this is, I think, part also of the lesson of these connections. And these are the kinds of connections which I think really form our subject of physics, these connections between different patterns. And actually, I've talked about this in this hall at various times. So this is what I call looking at patterns and seeing commonalities in patterns, and then seeing what is the underlying mechanisms and what is the essence that is actually leading to these results. So with that, let me stop. And I know you also have to run, but the rest, any questions that you have, so you're excused.
Thank you very much. Before time, so we can
Sadiq can, yeah.
Oh, coordinate first 5 minutes drive. Questions starting from the back row. Oh, Varuna one. Nobody from the go on.
Yeah, so in this maneuver, it looks like what is 60 degrees to do it? I see that it starts turning after 90 degree in
Well,
this
it
picture.
actually, the point is that it takes a little time for the ship to respond.
Okay.
And that's the reason to get a smooth turn, what you're doing is you're covering 1/4 of the circumference on the first circle,
Okay.
3/4 on the other. In a sense here, 60 degrees is not that critical, but
Okay.
that is simply dictated by the turn. But you have to make a jump from
Okay.
one circle to the next.
Okay.
And you have to do that by doing that turn.
Okay. So if we do that, then the time come to be minimal, is it?
Yes, this time is much less than if you try to come to a stop and then turn around and come back.
Okay.
That is much, much longer. So
Yeah.
that's why this maneuver is the one that they teach. Oh, incidentally, I think I skipped one last slide, and I should do this. I should show you this because in this audience, if the director, Radhakrishnan, Rad, who was here in '73, were here, he was a yachtsman. And he used to sail yachts even on the high seas. And actually, my younger boy does the same. He is a yachtsman, and they pointed out, or my son pointed out, and I'm sure Rad would have immediately recognized this, that if you're in a sailboat, there's one other constraint you have to be very careful about. And that's, again, very obvious to us. You have a sail, and the wind is catching it. You don't want to make a turn where suddenly the thing is spun around. And that is actually a mechanism which is called a jibe. Because what happens is that when you have a sail, there's a big boom which is holding that sail. And if you suddenly catch the sail turning around, that boom will sweep across your deck. And that can be very dangerous. And that maneuver is called a jibe. And at all costs, you have to avoid that. But still, the one that they recommend, in fact, my son had to undergo some tests just a month ago to keep his certification, and they, again, make them do this turn, which is, again, a double loop, and not necessarily the 60 degrees, but the main constraint here is that at all positions, the sail is never going to go sweeping across the deck. So this is a constraint, of course, for yachts, but for big ships, container ships, battleships, this doesn't come in. Yeah.
Thank you.
So, at the beginning part of your talk, you made an equivalent with electron, kilo electron volt with alpha particles in
Right,
mega
right,
electron
right,
volt.
right.
So, that physical motivation I wanted to understand. Means
Oh, you mean that equivalence?
Yes.
It's simply matching velocities.
I see. Okay.
But it's a very good rule of thumb. You should remember that a 1 kilovolt electron, for many purposes, is like a couple of MeV protons or neutrons. Or the same amount for alphas, because they're about the same, slightly more. But it's the kind of numbers that I think students should sort of, imbibe. That. So again, the first Bohm approximation, therefore, is great if you have more than a 2 MeV proton incident on an atomic system.
So this is related to this turning maneuver only. So what is the value of R one will choose in this? Is there any
No,
any
it doesn't
specific
matter.
thing? It could be any
It just
R.
has to do with the swinging of a ship. So what is the turning radius of a ship will determine that R.
Okay.
Yeah, the R itself plays no role. Yeah, and
So
again, as you know,
It could be
turning
any,
radius is-
any R in principle
Right, right.
with a minimum
But whatever
value.
it is, what you will see is that, for instance, the comparison is to go that distance d, which is roughly 2r, that's of course also the 2r, which is along the circle, that's much better than trying to come to a stop and come back.
I agree, yeah.
Sure, please.
So in that scattering problem,
Yes.
so that second scattering, it comes out to be 60 degree, right?
Right. Both scatterings. In fact, let me go back.
So what is the philosophy there? I mean, what is trying to minimize something or something?
No. I'm just applying momentum conservation and energy conservation here,
Yeah,
and I'm doing the same thing here.
yeah,
And you see, this is, of course, a given, the initial velocity.
yeah.
But I have unknowns, which is this velocity, and this velocity.
Okay,
And I want these, of course, to be the same, so that this is the electron and this is the B ion, and they are going to have the same velocities and they will capture.
Okay.
With that setup, I have 6 quantities which I want to calculate. I applied the 6 conservation laws here and here.
Okay.
And I just did the algebra to get what I got here for the values of the speeds and the values of the angles. And this angle then comes out to be 60 degrees. That's the same angle here as well, of course. So this gets hit by 60 degrees, and now this is turning it around by another 60 degrees, plus this little epsilon,
Okay.
and that is what is matching the two velocities.
Okay.
Hello, sir. Why that 25th term of the perturbation series is diverging? Means, is there any physical reason to diverge?
That's a very interesting question. Most series actually that we know seem to be divergent series. And actually, I'll give you one example where you can understand what has happened physically. And that is, go back to my simple hydrogen atom in an electric field. The hydrogen atom in an electric field, when you first look at the terms, they actually look quite well behaved. They're getting smaller and smaller, particularly for a weak electric field. When you put in, it's getting higher and higher powers of it. But then the coefficients start expanding after you hit about 20 or 25 terms in the perturbation series. And then, even for the weakest electric field, the series doesn't converge. Now, why? There I can give you a nice physical example, physical answer, because if you think about a hydrogen atom, the electron is bound in a Coulomb potential, but now you put an electric field. If you put an electric field, as you know, it's a linear potential. So on one side, if it rises, on the other side, it falls. So technically, no state is bound anymore, because quantum mechanics allows you to tunnel through that barrier and escape. So you've really changed the nature of the problem. It's no longer a bound state being slightly perturbed. It's not even a bound state problem anymore. And that is what that divergent series is telling you. Now, the remarkable thing is that mathematicians have invented a trick. They call it Padé approximation, some of you may know, which allows you to write a divergent series as the ratio of 2 polynomials, which mock it very well. But then if you look at those polynomials, it turns out that actually they can even be complex. So what happens when you sum this is that you get a real and an imaginary. The whole thing looks like magic at some point. It's all real stuff that you're doing, calculating electric field matrix elements to higher and higher order. But the whole thing sums to a real part and an imaginary part. And now I can give you the physical meaning. The real part is that slight change in the energy of any of these energy levels that the electric field has caused. The imaginary part also has a meaning, because as you know, an imaginary energy is a damping. So e to the minus IET now becomes, with an e having an imaginary part, e to the minus gamma t. That becomes the lifetime. So you actually get the lifetime of that tunneling out of it. So that is the, at least in that problem, that is answering for you what the divergent series is actually saying. It's saying that the problem has changed, the spectrum has changed, but you can still interpret it. You can interpret the real part, and the perturbation is good. The real part says it's only changed slightly from its original position, each of the bound states. But now they also acquire a little width, which is the lifetime of that state. And so that's a beautiful example, actually, where you can give you a nice physical picture.
So is there any rule to when it will diverge at which term?
No, no. Every series you have to examine, whether it's a convergent series or not. Some series are convergent, but this is an example. Many of these examples, however, are divergent. The Born series itself, we don't know. Nobody has proved for sure whether the Born series converges. And of course, you can't say it in general. You may be able to say it for some specific cases, that in this particular case, the series is convergent. But people really haven't even got to that. So what most people do in the field, I think others can vouch, is they just do the first Born approximation.
Thank you.
Further questions? If not, I'll just ask one while people are thinking about things. So when you talked about the second Born approximation, you talked in the context of charge exchange in heteronuclear species. Now that's a very specialized case for the application of this. And the point is, so I want to, because you are talking about patterns and stuff like that, I mean, if you are, I strongly suspect this is not generalizable in, the problem at C of turning a full circle at C versus, and a second bond. I mean, this is not a generalizable situation in any respect, or am I...
you mean I may
Just
not
a second
always
bond.
find a classical error?
Just a second bond.
Absolutely.
Yeah, because since there are a lot of students here,
Right.
I just want to point out that this is what at least I would categorize as an accidental degeneracy.
Well, you could also say that, or you could say we are very good at pattern recognition. So as I read the John McPhee article, I made the connection for that particular pattern recognition. But you can also go wrong if that's the warning you want to get to the students. Sometimes it can also lead you astray. But often, if you look at it, you'll either find out why you are not going to work or why it works. And in this particular case, I think the 60 degrees is the clincher of why that angle, even though it's not a measurable thing for you as an experimentalist, but indirectly we know that it's correct.
Sure.
The picture is correct.
If there are no further questions, let us thank Professor Ravi Rao for this wonderful lecture. And as a token of RRI's appreciation,
Yeah.
as a token of RRI's appreciation, we present you this book.
Thank you very much.
I
Thank you all.
hope you do not already have it.
I
think
do not
it's a
already have
relatively
it.
new publication
Right. Okay.
because you're older than most of these people.
Right.
Your
Right.
association with RRI is older than most people in this room.
Right.
So
When I first came to RRI, as I mentioned, which was over 50 years ago, there were only two people here, the director and one other. And of course, they're all gone now. And so even the staff and the library staff, and so I probably outrank almost everyone here. Right.
okay, so there's a possibility that there is a high tea downstairs. I cannot vouch for it since I didn't organize it, but other colloquium committee members may actually intervene. So let us try our luck and see if there's a high tea downstairs, and everyone is welcome. Thank you.
Thank you. Huh, this is a nice book.
This is a nice pictorial,
It's a very nice book, yeah.
thing. I mean,
No, I hadn't even seen this.
No, it's a recent. I think it's more recent.